In the last few lectures, we have studied the Fourier transform of a function, where what we have done actually, we have studied how to find out the Fourier transform, how to find out the Fourier cosine transform or Fourier sine transform of a function. Then we have studied the properties of the Fourier transform, which includes the scaling property, shaping property and other properties. And also, if I know the Fourier transform of a function, how to find out the differentiation of the Fourier transform of the function or integration of that function, Fourier transform of integration of that function, that also we have studied. Afterwards, we have studied the convolution and the convolution theorem, how to define the convolution of two functions, if you remember f star g, and then also we have studied the after convolution Parseval's theorem. And now we are going to study what are the applications of the Fourier transform and Laplace transform. The first one which we will study is the application of Fourier transform to ordinary differential equation. If you recall, we have done the similar thing for the Laplace transform also, that is how to find the solution of ordinary differential equation using Laplace transform. That thing we have done. So, now we will first study how to find out the solution of ordinary differential equation, mostly the second order ODE, using the Fourier transform without using the concept of CF and PI. So, let us see the first example on this one. So, the first topic is application of Fourier transform to ODE. Here we have to find out the solution of the ODE, which is given as this minus d2 u. This actually will be the other one, d2 u dx square, not du square, this one, and plus a square u equals some function of x, where x lies between minus infinity to infinity. So, your problem is this one. If I take the Fourier transform on both sides of the given equation minus your Fourier transform is equation is d2 u by du square plus alpha square u, this is equals to some function of x, sorry, this is some function of x, and please note that we have mistakenly written this one. This will be d2 u dx square plus alpha square u, this is equals to f x. So, now you take Fourier transform, on both sides of given equation. If I take the Fourier transform on the both sides of the given equation, what I will obtain is minus Fourier transform of d2 u dx square plus alpha square can come outside Fourier transform of u. This is equals to Fourier transform of f of x. Please note this one, that Fourier transform of dn or Fourier transform of f n x, if I write it in the smaller notation, this is equals to minus I alpha whole to the power n into f of alpha, where your f of alpha is the Fourier transform of f x. This thing we have done already. So, please note this formula, that Fourier transform of f n x, this is equals to minus I alpha whole to the power n into f alpha, where f alpha is the Fourier transform of f x. So, if I use this one, then this becomes minus, this will be minus I alpha whole square into say u alpha, I am writing capital U of alpha, plus alpha square into capital U of alpha. This is equals, I am writing f of alpha, capital F of alpha, where your Fourier transform of small of u x, Fourier transform of small u x, this is equals capital U of alpha, that is Fourier transform of u x equals u alpha and Fourier transform of small f(x). If I write down this, Fourier transform of f(x), this is equals to capital F of alpha. So, we are using this Fourier transform of ux equals capital U of alpha, Fourier transform of f(x) equals, this is equals to f of alpha. Once I am using this one, so therefore, I can simplify this one, I can take capital U alpha as common and I can write down U alpha equals capital F of alpha by, here it will come alpha square plus, sorry, this I have made a mistake, this is not alpha square, this is a square. So, this will be a square and this is also a square. So, that it will be alpha square plus a square. So, please note the changes. The problem is minus d2u dx square plus a square u equals some function of x. Taking Fourier transform on both sides, I am getting this, and ultimately I will obtain u alpha equals f of alpha by alpha square by plus a square. So, effectively what you are doing, whenever I want to solve a problem of second order ODE, first you take the Fourier transform on both sides of the given equation, use the formula that Fourier transform of f n x equals minus I alpha whole to the power n into f of alpha, then simplify it using this formula and you will get some equation of the form 1 of the type u alpha equals f of alpha by alpha square plus a square, where capital U alpha is the Fourier transform of small ux small u and the capital F of alpha is the Fourier transform of f of x. Now, from equation 1, if I take the inverse Fourier transform, in that case you can obtain u of x, this is equals, you can write down Fourier inverse of f of alpha into 1 by alpha square plus a square. Using from 1, using the inverse Fourier transform, always we can write down ux equals Fourier inverse of f of alpha into this alpha square. Now, if you recall the Fourier inverse of this is equals from the convolution theorem, this equals, you can write down minus infinity to infinity f t into g of x minus t dt. G of x minus t dt, using convolution you can write down this thing that 1 by root 2 pi minus infinity to infinity f t into g of x minus t dt, where your g x is nothing but Fourier inverse of this function, that is 1 by alpha square plus a square, and already we have done this thing, the value is 1 by a root pi by 2 into e power minus a into modulus of x. We have done already this thing. So, g x is Fourier inverse of alpha square plus a square, which if I evaluate, I will obtain 1 by a root over pi by 2 e power minus a into mod of x, and your f x f t is nothing but your f x is the Fourier inverse Fourier transform of f of alpha. This I am not writing. So, please note that your f x is Fourier inverse transform of f of alpha and g x is this. So, that once I obtain g x, I can obtain g x minus t also. So, this equals 1 by 2 a root over 2 will come, root pi will be cancelled over here, minus infinity to infinity f t into e power minus a into modulus of x minus t into dt. So, once I am obtaining this, then I can obtain this integral 1 by 2 a minus infinity to infinity f t into e power minus a into modulus of x minus t dt. Please note that I have solved a generic problem by taking the function f x. We cannot evaluate this integral integration further because the function f x is known to us at present. Once f x is known to us, then we can evaluate the integral and I can tell what is the value of the u x. So, please note that to find out the solution of the ODE using Fourier transform, you take the Fourier transform on both sides of the given ODE, then you will find a equation of the form of 1, that is capital U f alpha equals some function you will obtain, where u alpha is nothing but the Fourier transform of small u x. Then you take the inverse Fourier transform to find out the u x and to evaluate the integral. Sometimes you may have to use the convolution theorem, just like we have used over here. Fourier inverse of f alpha into 1 by alpha square plus a square. This equals, we have written this using convolution theorem. So, just quickly let us see this one. So, this is a mistake over here, d2u dx square will come. So, we are taking the Fourier transform minus Fourier transform of d2u dx square will come plus a square into this. So, please note that Fourier transform of f n x equals minus I alpha whole to the power n f of alpha. So, I am just putting this value and I will ultimately obtain u alpha equals f of alpha by alpha square plus a square, where capital U of alpha is Fourier transform of u x and capital F of alpha is the Fourier transform of the function f of x. So, always we will obtain some equation like this. Once I am obtaining this, then u x can be obtained from this equation 1 very easily by taking the inverse Fourier transform, that is u x will be Fourier inverse of f of alpha into 1 by alpha square plus a square. So, this is of the form of Fourier inverse of f x into g x form. So, this I can write down 1 by root 2 pi minus infinity to infinity f t into g of x minus t dt, that is convolution of those two functions f and g, where your g x is nothing but Fourier inverse of 1 by alpha square plus a square, and which I evaluate the Fourier inverse, which already we have done it. This is equals 1 by a root over pi by 2 e power minus a into mod x. So, now substitute the value of g x and I will obtain after simplification u x equals 1 by 2 a minus infinity to infinity f t into e power minus a into modulus of x minus t into dt. And once the function f t is or f x is known to us, in that case always we can evaluate the integral and we can tell the exact value of the function u x. So, this is the process for evaluating one ODE using the Fourier transform. Now, let us take some more examples. Now, you consider this example twice, because the earlier one what we did was generic one. Now, let us take another one, say twice d2y dt square plus dy dt minus 3y equals e power 5 I t. This is the ODE which we have to find out. So, ultimately our aim is to find out the value of y t. So, you take Fourier transform on both sides of the given equation, and by knowing that Fourier transform of y n t equals minus I alpha whole to the power n into y alpha, that is, again I am writing so that you can remember it. Fourier transform of y n t, this is equals to minus I alpha whole to the power n into y alpha, where your y alpha is nothing but Fourier transform of y t. So, that it will be clear to you that y alpha is Fourier transform of y t. So, now if I use this formula and take the Fourier transform on both sides of the given equation, then 2 into d2y dt square will be minus I alpha whole square into y alpha. So, 2 into minus I alpha whole square into y of alpha plus dy dt is there. So, dy dt means n is 1. So, it will be minus I alpha into y alpha minus 3 into Fourier transform of y t, that is, you can write down 3 into y of alpha. This is equals to Fourier transform of e power 5 I t. So, this is equation 1. Now, very first thing what I have to do, I have to find out the Fourier transform of e power phi by t. Otherwise, I cannot proceed here, because this left hand side always I can write a function of y alpha, but first job will be to find out the Fourier transform of e power phi I t. Now, if you recall, Fourier transform of e power I a t into f t, this is equals f of alpha plus a, capital F of alpha plus a, where capital F alpha is nothing but Fourier transform of small f t. If you recall, we have done this property earlier, that Fourier transform of e power I a t into f t, this is equals f of alpha plus a. So, now on this you put f t equals 1 and a alpha equals 5. So, therefore, what will happen over here? Your f alpha is what? Your f alpha is nothing but Fourier transform of f t, and f t we have assumed as 1. So, that this you can write down, this is equals Fourier transform of 1. Now, Fourier inverse of, you start from here, Fourier inverse of root over 2 by pi into Dirac delta function, this is equals from the definition 1 by root 2 pi minus infinity to infinity root over 2 by pi into Dirac delta function, which will be alpha into e power minus I alpha t into d alpha. And this is nothing but, so just we are writing Fourier inverse of Dirac delta function into root 2 pi. This is equals, you are getting this, and this equals minus infinity to infinity Dirac delta function into e power minus I alpha t into d alpha, which already we have obtained. If you see earlier lectures, the value of this integral is nothing but 1. So, that we are obtaining that Fourier inverse of root over 2 by pi into delta t, this is equals to 1. So, this we have proved over here. So, I am rewriting this, that Fourier inverse of root over 2 by pi into Dirac delta function, this is equals 1. So, that if you take the inversion, then I can write down Fourier transform of 1 is nothing but root over 2 by pi into Dirac delta function, that is delta of alpha. So, therefore, your f alpha will be nothing but f alpha, that is Fourier transform of this is equals to Fourier transform of 1, and this is your root over 2 by pi into Dirac delta function of alpha, which says that f of alpha plus 5, f alpha already we defined, f of alpha plus 5 will be root over 2 by pi Dirac delta function of alpha plus 5, and which implies that your Fourier transform of e power 5 I t, this is equals to root over 2 by pi into Dirac delta function of alpha plus 5, because in the equation 1 we assumed that I have to find out Fourier transform of e power 5 I t. So, that Fourier, this is not alpha, but this will be t, Fourier transform of e power 5 I t, and we have shown that Fourier transform of e power I a t f alpha, Fourier transform of e power I a t into f t, this is nothing but f of alpha plus a, and f of alpha plus a is nothing but, we have shown f of alpha plus 5 is root over 2 by pi delta alpha plus 5. So, that from here we can tell that Fourier transform of e power 5 a t, this is nothing but root over this one, root over 2 by pi delta plus 5. So, once I have obtained the Fourier transform of e power 5 I t in equals root over 2 by pi into Dirac delta function of alpha plus 5. So, from 1 you can write down like this. Left hand side will be 2 alpha square plus I alpha plus 3 into y alpha. This is equals root over 2 by pi Dirac delta function of alpha plus 5. So that your y alpha, which is nothing but Fourier transform of yt, this will be equals to minus root over 2 by pi into Dirac delta function of alpha plus 5 by 2 alpha square plus I alpha plus 3. And if I simplify it, I will obtain minus root over 2 by pi into Dirac delta function of alpha plus 5 divided by alpha minus I into 2 alpha plus 3 I. I am obtaining this. Therefore, this again I can break it 1 by a into b format is there. So, using componendo and dividendo I can break it into two parts in plus minus sign. So, once I am doing it, I can write down Fourier transform of yt. Fourier transform of yt, this is nothing but equals to y of alpha. This will be equals to minus root over 2 pi by 5 into delta alpha plus 5 by I alpha plus 1 minus delta alpha plus 5, which is there on both, by I alpha minus 3 by 2. So that once I have breaked it and I know Fourier transform of yt, which is y alpha, is this. Now, by taking the inversion, I can tell that yt equals Fourier inverse of minus root over 2 pi by 5 into Fourier inverse of this thing lambda delta or Dirac delta function of alpha plus 5 by I alpha plus 1 minus Fourier inverse of Dirac delta function of alpha plus 5 by I alpha minus 3 by 2. So, I am obtaining this. So, once I am obtaining this, now basically what I have to do? I have to find out what is the Fourier value of this function, Fourier inverse of Dirac delta function of alpha plus 5 by I alpha plus 1. For that one, from convolution theorem, you know this thing which we have used earlier, Fourier inverse of f of alpha into g of alpha, which is equals to f star g of t, f star g, and this equals, you can write down 1 by root over 2 by pi minus infinity to infinity fu into g of t minus u du. So, I will use from the convolution theorem this form Fourier inverse of f alpha into g alpha, which is there, where f alpha will be Dirac delta function of alpha plus 5, g alpha will be I alpha plus 1, which I can write down f star g, and this is equals, we can write down 1 by root 2 pi minus infinity to infinity fu into g of t minus u into du. So, now this Fourier inverse of Dirac delta function of alpha plus 5 by I alpha plus 1, this I can write it as Fourier inverse of this. I am doing it in detail so that you can understand properly, and this will be 1 by I alpha plus 1. So, that your I alpha, your f alpha is nothing but delta alpha plus 5. Your f alpha is delta alpha plus 5, and from here, since f alpha is delta alpha plus 5, so you can write down, basically I have to find out f and g. So, from these two functions I have to find out small f and small g. So, that we are doing now. F t equals Fourier inverse of f alpha, and Fourier inverse of f alpha means nothing but Fourier inverse of Dirac delta function of alpha plus 5, and I know the value of Dirac delta function, which I am putting directly 1 by root 2 5 into e power 5 I t. In the last example itself we have done this thing. Therefore, since here f alpha is Dirac delta function of alpha plus 5, using the inverse Fourier transform, I obtain the value of f t as 1 by root 2 pi into e power 5 I t, and also g alpha is 1 by I alpha plus 1. So, let us see what is g alpha. G alpha is equals to 1 by I alpha plus 1, which tells you that your g t, small g t, is nothing but Fourier inverse of capital G of alpha, which is again Fourier inverse of 1 by I al 1 plus I alpha. If you evaluate this, again these things we have done, this is equals to minus root over 2 by pi e power t into h of t, where h of t is nothing but the Heaviside unit step function. H of t is nothing but the Heaviside unit function, which you know that h of t equals 1 for t greater than 0 and 0 for t less than 0. And this thing again I am repeating, we have done it earlier. In the earlier lectures you will find this result. So, I obtained f t and now I obtained g t also, and once I have obtained f t and g t, then Fourier inverse of Dirac delta function of alpha plus 5 by I alpha plus 1. This I can write down 1 by root 2 pi minus infinity to infinity e power 1 by root 2 pi, one more will come here for f. So, 1 by root 2 pi into e power 5 by u will come, and then again your g t minus u is nothing but minus root over 2 by pi into e power t minus u into h of t minus u into du. So, please see this one. This equals, we are using the convolution theorem, we are writing it f star g. F star g is nothing but 1 by root 2 pi minus infinity to infinity f u into g of t minus u du. Now, f t we obtained, g t we obtained, now we are substituting these values. So, this equals minus 1 by root 2 pi, 1 minus will come outside, and then I will write down minus infinity to infinity e power 5 I u into e to the power t minus u into h of t minus u du. And this h t is value is 1 when t greater than 0 and it is 0 for t less than 0. So, for t minus u it will be from t to infinity. So, that you can write down e power minus t will come, e power t will come outside, e power t by root over 2 by pi, and this I can write down from t to infinity. So, that it will become this t to infinity, the value is 1 e power 5 I minus u into du. So, here you please remember that in this range the value of this Heaviside unit step function is equals to 1, that we have put. Now, this is a e power function. So, that I can obtain the result very easily. I am directly writing the result of this integration. You will obtain it as e power 5 I t root over 2 by pi into 1 minus 5 pi. So, therefore, Fourier inverse of Dirac delta of alpha plus 5 by I alpha plus 1 equals e power 5 I t root over 2 by pi 1 minus 5 I. On the same way, if I proceed, then you will obtain Fourier inverse of Dirac delta function of alpha plus 5 divided by I alpha minus 3 by 2. This will be, you will obtain as minus e power 5 I t divided by root over 2 by pi into 5 I plus 3 by 2. This we have not shown. On the same process what I have shown earlier, you can get this particular result. So that now you can write down your yt because you got both the values Fourier inverse functions. So, this will be equals to minus root over 2 by pi e power 5 it divided by root over 2 by pi into 1 minus 5 I plus e power minus was there. So, it will be plus e power 5 it root over 2 by pi into 5 I plus 3 by 2. And if I simplify this one, ultimately I will obtain minus half into root over 2 by pi will get cancelled, e power 5 it will be common, and 1 by 1 minus 5 I into 5 I plus 3 by 2. And so, basically using the inverse Fourier transform, you are obtaining the value of the variable yt as this. So, in the next lecture also we will do 1-2 more problems, so that you can understand how to find out the solution of ODE using the Fourier transform.